What if you could actually hear the Big Bang? Not just see its afterglow in a telescope, but literally listen to the sound of the very first moments of creation. Well, get this. That's not science fiction anymore. It's the absolutely audacious goal of a project that's building the most sensitive ear in human history.
You know, for centuries, we've been all about building better eyes to see the universe, bigger and better telescopes. But this is something else entirely. It's about learning to hear the silent vibrations of space-time itself, the echoes of the most powerful events since the dawn of time.
So how in the world do you listen to the cosmos? Well, first, you've got to know what you're listening for, and the answer is something amazing called a gravitational wave.
Okay, imagine you drop a stone into a perfectly still pond. You see those ripples that spread out? That's kind of like gravitational waves, except the pond is, well, it's the entire universe. And the stone is something unimaginable, like two supermassive black holes spiraling into each other. These waves travel for billions of years, carrying a perfect recording of that cataclysmic event.
But here's the crazy part, the real paradox at the heart of this entire mission. The biggest challenge isn't out there in the vast, silent emptiness of space. Nope, it's the constant, chaotic noise right here on our own planet.
The scale of what we're talking about is it's almost impossible to get your head around. The ripple in space they're trying to measure is millions of times smaller than a single atom. This is, and I am not exaggerating, the most precise, most delicate measurement humanity has ever attempted.
And that's our big bad guy in this story, noise. You see, the Earth is never still. It's constantly vibrating, from ocean waves crashing on distant shores, from the wind, even from a truck driving a few cities over. All of that earthly vibration is a deafening roar that completely, totally drowns out the faint cosmic whisper we're trying to hear. Let me put it this way, because this analogy is just perfect. Trying to detect a gravitational wave on Earth, it's like you're standing in the middle of a massive music festival in Amsterdam, and you're trying to hear a single person whispering in New York. Yeah, it's that insane. You don't just need a good microphone, you need to build the quietest place on Earth.
So, how do you even begin to build the quietest place on the planet? Well, for the answer, we have to go to Maastricht in the Netherlands. That's where scientists are building something truly extraordinary. They call it an Olympic training camp for the technologies that will finally let us hear that cosmic whisper.
This is ETpathfinder. Now, this isn't the final detector itself, okay? Think of it more like the crucial testbed, the proving ground, where scientists are inventing and perfecting the radical new technologies they need for the main event, the future Einstein Telescope. That's going to be a massive 10-kilometer-long detector buried deep, deep underground.
So how are they going to defeat this monster of noise? It all comes down to a three-pronged attack. A trinity of innovation that targets the very laws of physics at their most fundamental level.
The first weapon in this fight is cold, unimaginably cold. Just look at that number. We're talking just a few degrees above absolute zero, the point where all atomic motion is supposed to stop. So why go to such an extreme? Well, it's all to solve a sneaky problem called thermal noise.
See, even in a perfectly isolated detector, the atoms that make up the mirrors themselves are constantly jiggling around just because of heat. Think of it like a busy crowd on a square. Even when they're standing still, people are shifting their weight, moving slightly. Those tiny atomic vibrations create a constant whisper that's still loud enough to completely ruin the measurement.
And the solution is just so clever. By cooling the mirrors down to minus 263 degrees Celsius, the scientists are basically forcing the atoms into a cosmic scale mannequin challenge. They become so still, so quiet, that their thermal whisper just fades away, revealing that even quieter sound from space.
But as always in science, you solve one problem and you create a brand new one. You can't use normal glass mirrors for this. They'd shatter into a million pieces at those cryogenic temperatures. The best material is pure silicon. It's perfect when frozen. But to our normal laser light, a silicon mirror is as opaque as a brick wall.
So there's your paradox, right? You've built this perfect ultra-cold mirror to listen to the cosmos, but now you can't even shine your laser on it to take the measurement. It seems like a total dead end.
The solution, though, is wonderfully elegant. You don't change the mirror, you change the light. The team at ETpathfinder developed a special laser that uses a specific wavelength of infrared light. And to this invisible color of light, the silicon mirror isn't a brick wall at all. It's a perfect, crystal clear reflector.
Boom, problem solved.
So, with these incredible technologies perfected, the ultra-cold mirrors, the invisible lasers, the whole shebang, what does the future actually sound like? Let's zoom back out from the lab in Maastricht, all the way out to the entire cosmos.
And this really puts it all into perspective. The amazing James Webb Telescope can see the light from the very first stars, right? That's about 200 million years after the Big Bang. But the technology from ETpathfinder will allow the Einstein Telescope to hear the gravitational waves from the Big Bang itself. We'll be able to probe and mirror before light, before stars, literally listening to the universe just moments after it was born.
And the payoff is just immense. I mean, yeah, hearing the universe's birth is the ultimate prize, no doubt. But along the way, we'll be able to map every single black hole collision in the observable universe. And this is really important. The technology developed to achieve this, the ultra-precise lasers, the vibration-free cooling, it has incredible spin-off applications for industries like chip manufacturing and quantum computing, pushing the boundaries of what's possible right here on Earth.
And that's really the question that drives this whole thing, isn't it? For all of human history, we have been looking at the universe. We are finally on the verge of truly listening to it. And when we do, who knows what secrets it's been whispering all along.